Hello, welcome to Points of Topology and Video course. This is Shovik and Water Limits Customer Matters. This is the 11th session of Points of Topology, one course. So it will be a 1 hour session, okay? And and there will be two more session. One is upcoming, next Sunday, and another last session will be next week Sunday, okay? So there is still two more session left, okay? Okay, so before starting further, please let me know if you have any question or doubt. And before starting further, please let me know whether is the screen audible and is the screen visible and am I audible to you? Please let me know. There is one Mr. Joy check, Mr. Musta. Can you please confirm whether am I audible and is the screen visible to you? Can you please confirm? Mr. Musta, can you please confirm whether I'm audible and is the screen visible to you? Okay, I think everything is working fine. So so the screen has been presented. Hold a minute. Yeah. Okay. So okay. So today we'll solve some questions. So okay. So the first question is as follows. Okay. Um. So that the interval close 0, 1 uh, is these are some standard question you may face in your exams. Okay. So this close 0, 1 is a is compact. So the point is that of course I'm not going to bother about this how this will happen because that is true. So let just it's a sake of completeness I put this question. So let's change it. Okay. So think the next question. This sorry. What? Oh God. So this question does what? That show that open interval 0, 1 solves this topology is not compact. Okay. That means what? You need to exhibit an open cover which does not have enough finite subcover. Correct. So please think about and find out okay. So the hint has been given. Please try by yourself and figure out which finite subcover shall not work. Okay, the 1 by n comma 1 this will not work as per in the hint. Plus, but you please try to figure it by yourself or prove it by yourself. Else, I will present the proof. Okay, please take your time, think about it. Let me know. Please take your time. Please think about it. Take your time. Let me know. So here what you need to, you need to, here we have some open cover, you need to show that this is not a finite subcover. So what you need to do, you need to start by assuming that suppose it is finite subcover. Then you need to come up with some contradiction, correct? So please think about, let me know. Take your time. Pustak, any, are you able to figure out? Or any guess or any idea? So, okay, so let me press the argument, okay? Argument, I mean, so the, okay, so see, the argument is as follow. So we have the open cover, correct? Un, where un is equal to 1 by n, comma 1, right? 1, hold on, 1. Okay, so, hmm, hmm. So consider the open cover un is equal to 1 by n, comma 1, okay? Now, since u covers 0, I mean, of course, it's open cover, so nothing to prove. Now, if this un has a finitely many subcover, then what will you? We shall get some n1, some n1, n2, some n1, n2, nk, finite many, such that the union becomes 1 by n, correct? Now, since un is the sum of un, that means what? That the large capital M, if you consider 1 by 2m, this will lie outside one this union. So that means what? Open G1 is not compact, okay? That is the argument. So that's the thing. So is that clear? Please let me know. So basically, we are assuming the trick is the following. You are assuming the fact that it admits a finite subcover, correct? Okay. That means what? That means we shall always get u1 u2 un and m is equal to n1 into nk such that un1 union dot dot unk that is equal to 1 by m comma 1. But that means what? 1 by 2m belongs to 0 1, but that 1 by 2m does not belong to union. So that tells open G1 is finite, is not compact. So that is the argument. Okay. So that is the thing. Okay. Okay.
Yes.
So okay. So is that clear, Mustafa?
Yes. Yes.
Okay. Thank you for confirmation. Okay. So let's go to the next problem. So the next problem tells us follows up if is the map X to a continuous surjection, if it's continuous, prove that Y is compact. So this tells that continuous even a compact set is compact. We have already seen this, so we are not going to prove this anyway. Okay. So um, okay. So this question is interesting. Show that closed subspace a compact set is compact. So yeah. So please try to do yourself and hint is given. Please try see the hint and please figure this out by yourself. That means what? You need to construct an open cover of C. From that open cover also you need to construct an open cover of X. Then you need to use the compactness of X. And from that you need to conclude the compactness of C. Okay. So please think about take your time, let me know. And please use the hint given.
So
Yeah.
see, see here you take a close subset.
Yeah. Okay.
Let let UA be an arbitrary open covering of C in the subspace topology.
Okay.
For each UA, there exists an open set, suppose
Mhm.
V1 in X such that UA is equal to VA intersection C. So
Okay.
the set of open set VA union X minus C forms an open cover of X
Got it.
because the union of C and its complement is the full space. So
Got it.
secondly, because X is compact, so this covering of X as a finite subcover B A1, B2, A2, B except Bn and X minus C. Covering then since F is closed, the set X minus C does not contain any point of C.
Got
So therefore the set BA2, BS, especially in their intersection with C, must cover C. So
Correct.
we have concluded that a finite subcover UA UA1, U2, A2, UAN form the original arbitrary cover of C. Thus, C is compact.
Correct. Correct. Tony. Very good. Very good. Very good. Absolutely correct. So whatever Mustaq has explained is absolutely correct. So we need to basically start with the open cover of C, and then that open cover begins an open cover of X by adjoining X minus C. Now think X is compact, so that our new open cover will have a finite subcover. So that gives that C has a finite subcover. So that's the argument. Okay. So the next problem is as follows. I hope it's clear. So next problem is as follows. Suppose there is a Hausdorff which is K with a compact subspace. We need to prove that K is closed. That is compact subspace by Hausdorff which is closed. Okay. So please think about, take your time, let me know. That means what? So you basically need to show the X minus K is open. That means you need to show that there is an open cover in X minus K which is contained a line X minus containing a point of X. Okay. So please think and let me know. Take your time. So Musta, please try to figure out this problem. The hint is going. Please think and take your time. Let me know. So any idea how to approach this problem? We have explored this problem previously, but please think about and let me know. Okay, so let me explain this argument. So we assume that x minus k is open, okay? We choose that x belongs to x minus k. And in that case, what would be? We are separating each point of x outside of k. Now by Hausdorff, we get a set uk and vk, so the uk intersection vk empty. Now, for covering, we are considering all those open set v suffix k containing each k. So by finite subcover, there exists k1, k2, k. Sorry. By finite subcover, there exists k1, k2, kn such that k sub of vk1 union vkn. Okay. So that means we got a finite subcover of vk for each point of x belongs to u. Now, we are considering corresponding subcover uk1, uk dot ukn. And these are finite intersection open sets of x containing x. So that means what? U intersection k is empty, and if y belongs to u intersection k, then y belongs to vkj. But ukj intersection vkj empty is a contradiction. So that is the argument, okay? So that means what? That means uk intersection vkj is equal to empty contradiction, and u intersection k is equal to empty, right? So that means u open set containing x containing x. And since every open code x belongs to x minus k has such a neighborhood x minus k open, so that k is closed, okay? So that is the argument.
Yes, it's okay.
Is that clear?
Yeah.
Oh, oh. So, oh. So that tells that x minus k is open, this k is closed. And not only that, so now show, okay, so that this part is over. Now the next problem. Show that set of rationals is totally disconnected. That is in only in Q. The only kind of sets are singleton or empty sets, okay? So please think about take out tablet video. Think about take your time. That means what? You need to, if you need to choose any connected set, and if you assume that it is more than 2 points, then it cannot be connected. In that case, you can get disconnection. So that's what you need to prove.
Well, given any distinct rational number, suppose A and B belongs
Okay.
to Q,
Okay.
and A for assume A get A less than B. So there exists an irrational number alpha such that a less than alpha less than. So we can construct a disjoint open set using this irrational number. So we can partition Q into two non-empty subsets. Suppose U and V. The U, we can take U is equal to, is equal to open minus infinity to alpha of the intersection,
Okay, huh?
and V is open alpha to infinity intersection Q.
Correct.
Conclusion that we U and V both are open set in Q by the definition there by subset topology, and they are disjoint. They are
Correct.
disjoint. So their union is Q because no natural number is equal to air alpha since they can be done for any 2 points. So alpha
Correct.
they are arbitrary. So no subset with more than 1 point can be connected. So only point it is
Correct. Right. Absolutely correct. So here basically what we're doing, here's this A, so we choose A subset of Q to be connected. We choose rational number R. Then A can be written as A intersection R minus infinity, A intersection R comma infinity. And so that means what? So that means what? Those two pieces acts a disconnection of the set capital A, which contradicts the connectivity. So that's why Q is totally disconnected. So that is the argument. Okay. So this is the detailed proof. If you wish, you may go through the proof. Let me. I'm waiting for a few more minutes. Please think about it and please see the solution and let me know so that I can go for the next problem. So I hope you have gone through the argument. So let me go to the next problem. So the next problem is the routine problem. If with continuous of x is connected, then f of x is connected. I know there is a general theorem also, but it can be given an exercise. So please think or take your time, and it is unmute yourself and explain the solution. Okay. So please think it and let me know. It can be solved in two ways. One is that function method if going to plus minus zero method. Another will be like usual definition. Okay, please think and let me know. Take your time.
So first of all, we have given that f is a continuous function. Yes, and another is x is connected topological space. Suppose you take the image, where image is fx, z is equal to fx, with the image of x in y. From here, proof is that if suppose we take that fx is not connected, by definition we use the separation property. That there means any two empty subset, they are suppose A and B are open in the subspace topology of F.
Yeah,
And
correct.
the intersection B is Y, and their image is the full FX. Consider the pre-images of these sets under F. So the images, the F inverse A and F inverse B. Take just F inverse A is equal to U and E is equal to F inverse B because F is continuous.
Correct.
So the pre-image of any open set is always open. Therefore, this F inverse A and F inverse B are open in X. Now you have to check U and B. Then both A and B and non-empty subset of the image. So there must be points in X that map to them. Thus we must be U and B both are not phi. And A, B are this joint, so their intersection must be phi, and their pre-images must be also the disjoint U F inverse A and F inverse B equal to phi, and then a union
Mm,
A in A union B is equal to Fx, and their pre-images must cover the entire domain F
correct.
inverse A union F inverse B. So we can write is equal to F inverse A union B, and F inverse of F x is equal to x. We have found that the two non-empty disjoint open set F inverse A and F inverse union is x.
Mm,
This constitutes a separation of S, which means x is correct. This contradicts our early assumption that x is correct. Therefore, our assumption if x it is joint, it cannot be disconnected.
mm,
It must be correct.
correct. Correct. Very. Absolutely correct. Okay, so Okay, so now let me present the proof of this. Mustak's argument is absolutely correct. So this argument is as follows. Whatever he explained, everything is written here. Please go through the argument. If you wish, you can take a screenshot of the argument. Okay. But
Understand.
yeah, please go through the argument once again. So you may wish the argument. Okay, so let me go to the next problem. So next problem is suppose A and B are connected subspace of X and so A subset B subset A closure that B lies within A and enclosure. Then we need to show that B is connected. Okay. So for this argument, you okay, either go through definitions or you can use the function method. You need to choose the function f from b2 plus minus 1 and show that f is constant. Okay. So please think, take your time, let me know. So Mr. Please think and try, let me know. Take your time. Okay, so the argument is as follows. So by suppose by contradiction we are assuming, suppose by contradiction we are assuming that they are not as a U and B, so it's the U intersection. It's empty and B is equal to union. Now since A lies on one piece, now since A sub of B, that's the A sub of union, but A is connected. That means what? A sub of U or A sub of B. Okay. Now since A sub of U and U is open and V is empty, now B sub of U closure, A closure. Now since V is empty, so pick B belongs to V. Then B belongs to B sub of closure of A. So every open neighborhood of B intersects A. So V is open in B. So V is equal to W intersection B. Now since B belongs to closure of A, we get W intersection A non-empty. Pick A belongs to W intersection. That means what? A belongs to U intersection A, contradicting the fact that U intersection V is equal to empty. So that means what? B is connected. So that is the argument. Okay. So that is the thing. Is that clear, Mustaq? So yeah, so that's the arguments. Okay. So yeah, so is that clear, Mr. Mustaq? I hope so. Now, let's look at the first problem which you have skipped. I mean, of course, that's a theorem, but without use of let's. So here I have proved, I have showed another way of proving this. The closed interval G1 is compact. So of course you can use the Heine-Borel theorem to prove that, but apart from that theorem, you can use another creative way to solve this problem. Okay, so please do think and let me know. Okay, so The arguments are as follows. So here what we're doing, we're choosing arbitrary opens at UR. Okay. We're defining x to be closed interval 0, 1. All those x are that closed interval 0 to is correct finally being null. First of all, x is not empty. Why? Because I mean 0 belongs to 0, 1. X is not empty. Why? Because like I mean the interval 0 comma 0. So there is u alpha 0, so there is 0 belongs to u alpha 0. Now u alpha 0 is open in this, it contains 0 by epsilon. So any x belongs to 0 epsilon satisfied 0x above u of x. That means what? That tells x is non-empty. Now x is bounded above by 1. For x is bounded, there is no confusion. Now point is that we are trying to show that s naught belongs to x. That means what? Closed interval 0 comma s naught is finitely many. So u beta belongs to u. So s naught belongs to u beta. Since u beta is open in 0 comma 1, where since u beta is open 0 comma 1, that means what? We shall get a delta greater than 0, so the s naught belongs to delta minus plus s naught plus delta sub of u sub x of u. So by definition of superposition, that means what? S naught belongs to S with S naught with X naught greater than S naught minus delta. Okay. Now, since X naught belongs to S, so the interval 0 comma S naught, X naught is covered by finitely many sets from U. Say U alpha 1 dot or U alpha n. Then 0 comma S naught, these things, sub of U. Now, we are claiming that S not equal to 1. Suppose for contradiction X not less than 1, okay? That means what we can say? From this, we can say that S naught minus 1 plus S naught plus 1, and for any y belongs to S naught, minimum S naught plus delta, 1 satisfies 0, y sub of u alpha 1 or u alpha beta. So y belongs to S with y greater than S naught, contradicting S not equal to sup of S. So that tells that S not equal to 1. Okay. So therefore, 1 belongs to X, meaning 0, 1 is covered by finitely many members. Okay, now since U was arbitrary and 0, 1 is compact, hence we are done. So that's what the argument is. Okay. So now, so this is the another way. So instead of directly using Honey-Burger theorem, it's another way of doing this. Okay. Now, possibly this problem also skipped here. So, so in this problem, we are basically trying to show that surjective map image is also connected. Sorry, compact. Okay. So in the class, we have seen that this problem can be solved by using compactness. No, it's connected. It can be solved by compactness. Sorry, it can be solved by using compactness of closed interval 0, 1. But from definition also it can be solved. Then solution is as follows. Okay. So Okay, so this is so in this so basically in this problem what we're doing, we are choosing open cover V alpha, and we are considering the corresponding inverse image F inverse V alpha. Okay. Now, so that union of F inverse V alpha gives an open cover of X. Okay. Now X contains finite many subcover, so X equal to union of F inverse V alpha I equal to 1 to it. Okay. So that implies what? That implies Y is equal to V alpha 1 union dot dot of V alpha N. That is that Y is compact. Okay. So that is the argument. So that is the thing. Okay. Now, now, so that so this thing you have seen already. Okay, one more thing, observe that few of the connectedness problem has been done by using um, definition. Okay, but all of this connectedness problem can be solved by using the function method. That means choose a function f from the desired set to plus minus one and show that f is constant. For example, suppose f is a function from b to plus minus 1 where b contains c, we need to show that if b lies inside a closure, then f is continuous. Okay. Suppose if suppose b belongs to a closure. Okay. So that means what? B and there is a point A, so which is very near. Okay. Now for continuity, what will happen that from in B also it emits 1. Correct. So that's what the argument is. So is that clear? Now a subset of U and U is open. So that's what. So this is tells. Okay. Okay. So although I had not written that, but from the discussion of the sessions, it's clear that it can be done. Okay. That is one thing, as well as okay. Okay. So thank you for this session today. We shall meet on tomorrow from 7 to what? 7 to from 6 to 9, 6 to 8. Okay. If you have any problem, any doubt, please let me know. So if you have any doubt, please let me know, or else we can leave this stop session here. Please take your time and let me know. Okay, so I hope there is no problem. So if you have any problem, you can ask in tomorrow from 6 to 8 session. Okay. Okay, thank you. I'm leaving the session.